Now that we have seen how the real atmosphere changes, let's see how it can be modeled. But let's keep in mind why we want a model here. If we were to model all of the variations that we saw with latitude, temperature, etc., it would result in a very complex model. And instead we want a model to which we can reduce the data that we collect in flight test. A model that resembles the atmospheric variations that we saw, but does not need to capture all of the nuances. As always, all of the code is going to be in our GitHub repo, and the link is going to be in the description.
3, 2, 1, top.
3, 2, 1, half, the flight test engineering channel.
If we are going for the fundamentals, where better start than the equation of state, PV equals nRT. And before we start going into the equations, let me just create a new view here from my notebook so that we can keep an eye on the small volume, differential volume that we have created here, so that we have it all in our minds. And if we take the differential cylinder we have here with the height dh, we have gravity acting on this mass, creating a force that is going to be equal to the weight of the fluid. And on the extremities of the cylinder, we'll have pressure P on one end and P plus delta P on the other end. dP can be positive or negative, and we'll figure it out later. Don't worry about that for now. Let's write the equations for this. From the hydrostatic equation, we can then write that our weight is going to be minus mg, and mass is going to be density times volume, and volume is going to be area times height, so dA times dh. And notice that in this case, h here is our tapeline height. The sum of our forces due to pressure is going to be pdA minus p plus dp dA on both ends. So you can see that p cancels out, leaving us with just minus dp dA. And then when we sum up all forces, we're going to have sum of all forces going to be gravity minus dp dA, and they are going to be equal 0 because our cylinder is not moving. So dp, and from this we can write that dp equals minus rho g dh. And we could try to integrate this equation now, integrating pressure on one side and then minus rho g dh on the other one. But g varies with altitude, and so does our density. So we would have to do a numerical integration here, which is not nice. So we have a slight problem. And how does this gravity vary with altitude? If you go back to Newton's theory, it's going to vary according to the radius of the Earth divided by radius of the Earth plus whatever tapeline height you have. Everything squared. So that's what we're going to do. We're going to take the gravity at sea level, multiply by this term, varying our height to see what is our new g that we get. And we can do this, for example, at 55,000 feet. Let's see what we get. And if we define a conversion factor from feet to meters as 1 over this number, the radius of the Earth is going to be 6378000 meters. That's at the equator. Acceleration of gravity at sea level, my altitude is going to be 55,000 feet, as we saw. Then from here we can calculate directly with this formula. The g at my altitude is going to be g at sea level times this relationship. So if we run this cell, we get that the acceleration of gravity at 55,000 feet is going to be 9.755. So the difference in acceleration between sea level and 55,000 feet is going to be only 0.05 meters per second squared. Okay, now that we have seen this and we understand the differential volume here, we can close this window. And we can define a geopotential altitude h as g dh equals g at sea level times something else that we're defining as geopotential altitude. So essentially we're transferring the variation of g to a variation in height or altitude here. And we can then substitute this definition on the integral and get dh equals this relationship d small h. And now we can integrate on this side dh and on that side that relationship dh. But instead of doing this by hand, let's learn a cool trick here to do integrals and other calculus things in Python. Let's learn Sympy. Let's take this opportunity to learn Sympy. So what is Sympy? Sympy is a Python library for symbolic math, and it's not a fully featured computer algebra system yet like Maple or Mathematica, but it does a reasonable job. And in our case here, it will help solving this integral and maybe help you later with solving some more calculus. I will only brush on the basics here, just enough to get you started and just enough to solve this integral. There is a more complete tutorial by Mr. P Solver, and I based the following on his nice video. Go check it out if you want to learn more about Sympy, and the link, as always, is in the description. And first we need to import the library. So let's import Sympy as SMP here. And let's see a few basic operations. We can define a symbol. To define a symbol, we'll use that we will use in our equations just by declaring it like this: x equals SMP symbols, and in quotes x. And you can see that the x that is printed here is a little bit different. It's a little bit slanted because actually this is rendered in LaTeX. We can also define multiple variables here at the same time, like k1 and z, and when we put _1 here, you see what happens. Again, because this is rendered in LaTeX, it nicely renders k_1 or sub1 here. We can do simple math operations like squaring x or doing square root of x. And we can capture the result in a new variable like this. We can say that y equals x squared. And when we print y, it's going to be, of course, x squared. We can define polynomials, x squared minus 8x plus 12. Okay, and that makes it really simple now to get solutions. Notice that solve here takes the first argument as your expression equals to 0. And if you have an equation that has something equals something else, you can always transform it to something minus something else equals to 0. So here we have y equals to 0, and we're trying to solve for x. And of course, it's going to give you the two solutions that solve this equation to 0. We can take this polynomial, for example, and square it. Now get something like this. And now we can ask Sympy to factor this polynomial into the solutions that we already know are the two roots that we calculated before. Or we can even ask it to expand the polynomial into the full fourth order here. Now, Sympy will also make assumptions for the variables. And this is important because it will create bounds to the solutions. For example, if we don't say anything, Sympy will assume that x might be complex and present us with this. Right? We're defining x and we're trying to solve this equation. Sympy will present us with solutions including the imaginary number. Now, if we tell Sympy that x is real, then for the same equation, we should get nothing here as a result, because there are no solutions in the real domain here for this equation. And on a multivariable expression like this, we can define f equals x, something that depends on x, z, and y. We can solve f for x, or we can solve f for z. If we grab the first solution for z here, that's why we have two solutions, and by explicitly saying that we want index 0 here from our list, we get the first solution. And now we can use this solution to create a numerical function in Python that we can, for example, calculate values for with this expression _f. Here I take also the advice that Mr. P Solver sent by always using the same notation with this _f for numerical expressions in Sympy. And how does this work? Well, you call in the function lambdify, where you pass the arguments for the functions, x and y in this case, and then you pass in the expression, which is what we had before. And when you do this, Sympy will create another object with which you can call and calculate numerical values like this. Okay, enough for the basic stuff. What I love most is the calculus capabilities. For example, we can get the derivative of an expression by using the diff. So if we take the same expression f and differentiate with regards to z, we get this. And of course, the reason we went into this rabbit hole is integrals. And we can do the same here. We can integrate f with regards to z, and you get the expression. Now, in JupyterLab, an easy way to investigate which functions are available is to use the autocomplete by pressing tab after the dot. So let's try it here, but I need to zoom out just a little bit, otherwise it's not going to fit on the screen. So if I press tab, it's going to show you all of the available functions from Sympy. And you can explore each one of these and check out what they do. You can see it's a lot of functions, so it's a pretty complete library. The other thing that is important is that after you find a function that you want, you can read the doc string by pressing Shift Tab. So for the exponential here, if we press Shift Tab, it's going to bring up the doc string explaining what is the exponential function, how do you call it, what are some examples, what are the parameters, and so forth. So you can do this with any function. Okay, let me zoom back in. All right, so in our case here, let's define the symbols that we want, which are the radius of Earth, tapeline height and geopotential height. Let's tell that they are true and they're real and positive. And we can define the element that we're going to be integrating, like we saw from Newton's law. And now we can just tell Sympy to integrate dh with regards to h from 0 to h. And then you get this expression h, big H here, as the result. We can then tell Sympy to simplify this expression. And now we can again just create a function that is numeric so that we can maybe plot this. So let's lambdify this expression with arguments r, ESL, and h, small h. And the function we're lambdifying is big H to get an h_f function as a result. And now we can try to plot this. So we're going to import the usual NumPy libraries, matplotlib, and make it dark. We create the conversion factors, meters to feet, feet to meter, knots to meters per second, and so forth. And now here we're going to create an array that goes from 0 to 20,000 meters with a point every 1,000 meters. Okay? So that's an array that we can look at. And now what we need to do is define the radius of the Earth. And we're going to use the WGS84 geoid here. Because as you know, Earth is not a sphere and it's a squashed sphere. So the radius of the Earth varies as you change latitude. So taking the definition from WGS84, you have the semi-major axis A, semi-major axis B with these numbers. And we're going to take the latitude at 45 degrees, which is in the middle. With this, we can calculate what is the radius of the Earth at latitude 45 with the WGS geoid equation, which is here. And then we can finally calculate what is the age, resultant age, if we call our function for this radius of the Earth that we just calculated, for all of the tape line heights that we calculate with this vector here. And now we can plot here. What are we plotting? Our h resultant in from meters to feet, and then that against the difference between tape line and our geopotential height. Everything in feet now, okay? And this is what we get. We can see that we plot from 0 to roughly 55, 60 something thousand, And for instance, at 55,000, we have, at 50,000, we have roughly 120 feet difference between geopotential height and our tapeline height. We can rewrite the hydrostatic equation with geopotential height instead of tapeline height and divide by the equation of state to get a relationship between pressure and height that we can then integrate. And for the troposphere, we have the lapse rate. We can define the lapse rate, which is constant, and that is how temperature varies with altitude. We assume it is a straight line, giving us a relationship between the temperature at a height h and the bottom of that band. And if we can rearrange and integrate, we can then isolate temperature and then divide by T bottom here to get this equation. And then if we take what we had before and substitute this relationship, we end up with dP over P equals minus G at sea level over LR dt over T. We can then use Sympy here again to do this integral. So let's define P, P bottom, H bottom, T bottom, G at sea level, R and L. Here, we define the left-hand side as 1 over P, and the right, and then I'll already ask it Sympy to integrate it, and then define the right-hand side as this is constant, so I'm going to put it outside of the integral. So, and then integrate dt over t, just like so. Right-hand side, that's a constant times integral of 1 over t, and from t bottom to top of the band t. Notice that both sides have logs, so we can raise both sides to e to get rid of that. So we can take a look at the right-hand side, or left-hand side, and then right-hand side here. And notice that we have this exponent here positive because Sympy simplified to t bottom over t, but we want the opposite. We can just invert to t over t bottom and put in a negative g SL on top, right? So now we can equate right-hand side to left-hand side, and substituting t over t bottom from what we had, we can write p over p bottom equals a relationship between h and h bottom. We can further now simplify this by defining what is our band. And we can say that p bottom is our pressure at sea level, h bottom is going to be 0, which is our sea level, altitude is 0, and temperature at the bottom of our band is going to be temperature at sea level. And when we do this, we are defining the standard atmosphere. That's how we define what is the standard atmosphere. We also can define a pressure ratio delta equals P over P at sea level. And we can write the previous equation, this one, with this new definition of delta. So it's going to be delta equals something. Delta equals this much. We already know that h bottom is 0, so we can further simplify delta equals this equation. So finally, we are defining what is the pressure altitude as the altitude obtained from the standard atmosphere equation for a given pressure. And this allows us to directly replace our geopotential height here by pressure altitude that we're going to denote by HC. So this is the equation for our standard atmosphere, international standard atmosphere. We can also obtain the equations for density by using the equation of state. So it's the same idea, P over P bottom. And now we can fetch what we had before as defined so, and we substitute one into the other and end up with rho over rho bottom. And since we already had that equation from our lapse rate, we can substitute back. Again, define the density ratio sigma equals rho over rho at sea level, and we can write the equation for the standard atmosphere with regards to density. Okay? And the last ratio we define is for temperature, which is theta. It's the same idea, it's going to be T over T at sea level, And again, we had that equation that we defined with the lapse rate, and we can write for the standard atmosphere, theta equals 1 plus and so forth. For the stratosphere, it's even simpler because now temperature is taken as constant, resulting in these formulas after integration. You can read on the notebook, but it's pretty simple to integrate here. It's directly integration. You have logarithm on one side and then h minus h bottom on the other one. So it's going to be pretty simple. Same thing, same idea for the density equation. And the last thing that I want to touch base here is that sometimes it's useful to have the inverse relationship. So given a pressure, we want to know the pressure output that equates to. And manipulating the equations above, you can invert the relationships and end up with these results here. This for the troposphere and this for the stratosphere. I'll leave you with this table with a summary of all the equations that we have done the deduction during this video, so that we can use later to implement this in Python. Okay, and at the bottom, it's the definition of the base values for the troposphere and also for the stratosphere. In the next and final video of this mini-series on standard atmosphere, we'll implement these equations in Python. See you there!